Yes, good morning. Coming to the next topic of the fourth unit, that is VHDL description of 2-bit asynchronous up counter. Okay, asynchronous counter. It is in previous class. We have seen the operation of synchronous up counter, synchronous up down counter, and also asynchronous counter. Theoretical operation we observed now, and also we have seen the VHDL representation for the synchronous counters. Now, in this session, I would like to show how to write the VHDL program for the 2-bit asynchronous up counter. Okay, asynchronous case. Asynchronous, you know already, asynchronous circuit means that this is with reference to clock signal. The clock signal is applied to different elements of a circuit in different times. Okay, so that is the asynchronous operation. Okay, whereas in synchronous case, for all the elements, the clock signal is applied simultaneously. Okay. Now, the VHDL representation for this. So, in previous sessions, we have seen the operation of asynchronous counter. Let us see once it is a 2-bit counter like this. This is the asynchronous 2-bit counter. Already we discussed in last class. It consists two flip-flops because it is a 2-bit asynchronous counter. That's why it consists two flip-flops. Say this is the flip-flop D. This is another flip-flop D2, maybe. And if you observe the difference between synchronous and asynchronous is, I said that already, in the application of the clock signal. See, in a synchronous case, the clock signal is applied to all the elements simultaneously, but here is not like that. That you can observe here. This flip-flop has the clock signal from the directly source, whereas for the second flip-flop, the clock signal is from the output of the first flip-flop. Okay, it is from the output of the first flip-flop acts as a clock for the second flip-flop. Okay, so that's why it is referred as asynchronous counter. Okay, so for this type of design, how to write the VHDL program that we are going to see now. So as usual, you know the program will start with the library IEEE. Okay, then followed by library use IEEE.116 standard logic 1164.all like that. Okay, in addition to these two, one more package here is used from the same library IEEE, that is numeric standard. Okay, this is also another package. We put it in open mode. Okay, for the in order to execute this VHDL program simply. Okay, so library IEEE, then use IEEE standard logic 1164.all. All extension is generally we are using .all extension because if you use .all the declarations of this package will be in open mode for this program. Okay, similarly another package here we selected is, that is numeric standard. Okay, so total statement is use space IEEE.numeric_std.all semicolon. Okay, so these statements are compulsory for almost every VHDL representation. Then entity declaration. Okay, entity declaration start with the word entity, then its name is 2-bit asynchronous counter. 2-bit async counter is. Okay, this is the first line in case of entity declaration, the word entity followed by entity name. Entity name is user defined name. It is referred as identifier in the language, then is. Okay, then port of all input and output ports are declared in this port. Okay, port of X in standard logic. Okay, so X is the input, X is the data input, and clock signal, clock also input to the system. It is the clock signal to the system, and Q, another one is the signal is object is Q. Its mode is in out, but the data type is signed of 1 down to 0, because it is a 2-bit asynchronous counter. That's why the size is represented here as 1 down to 0, and the initial value assigned to this counter is 0 0. Okay, initially it starts from 0 0. That is the meaning of it. Okay, next another output port is there, that is Y with the mode out standard logic colon equal 0. That is, this output also having the value is 0 initially. Okay, so like that here, as per this diagram, whatever the diagram we observed in previous slide, it has two inputs like X and clock inputs and two outputs, those are Q and Y. Okay, so those are all declared now in the entity declaration. Then coming to architecture body, let us see the syntax of architecture body. Based on the syntax, it starts with the word architecture. Then architecture name here given as BEH, that means behavior of entity name. Okay, input is entity name 2-bit asynchronous counter is. Then if you have any declarations, that we have to place immediately after this line, but no declarations here. That's why begin word start. Actually, as per the syntax, before the begin, the word begin, we have the declaration statements. After the begin, we have the statements. Okay, since here no declaration, that's why after the first statement directly begin I have written. Then process, because since the model is behavioral model, in the behavioral model the concurrent statement is process. Okay, process of clock signal. Based on the clock signal, the counter operation will start. Okay. Then process begin. Actually, the process also having two parts, declaration and the statement part. Both are separated by the word begin. But here there is no declarations. That's why directly process begin have mentioned here. Okay. Then if falling edge of the clock, then okay, so after selecting the clock signal, whether it is in proper way or not, that is, our program is with reference to falling edge of the clock signal. That's why that falling edge also we are going to check. Otherwise, other than this falling edge, the clock signal, it may not do the following operation. Okay, so when the system clock is at the falling edge, then only the the entire circuit can do its function. Otherwise, no. Okay, so that's why if falling edge of clock is available, then after that we are checking if x equal to 1. If x equal to 1, x is the data input to the counter. If x equal to, then okay, if both are proper, that is clock signal is falling edge and x input is at logic 1, the output of the first flip-flop is u of 0 is not of u of 0. Okay, and if then since it is a 2-bit asynchronous counter, as you know already, if the count is at 1 1, the counter goes to the next state of 0 0. When it goes to the next state, the output value given as 1. Otherwise, it is 0. Right? So if q equal to 1 1, then q is assigned with the y is assigned with the value of 1. Else the y output is 0. Okay, then end if. So if x is not like that, then it doesn't go for the counting operation. So therefore, directly you can write here end if, and AND process. The end if statement is for this if, and this end if is for this end if and AND process. Okay. This is the program. This part of the program with reference to first D flip-flop of the asynchronous counter. Okay. Now coming to when the second D flip-flop can take its action is based on the value of q of 0. Okay, q of 0, because the q of 0 are the output of the first flip-flop acts as a clock signal for the second D flip-flop. So that now that output of the first flip-flop is used as a clock signal for the second one. Therefore, it is included as a sensitive input in the process. Now, let us see the VHDL representation for the second D flip-flop. So process of Q of 0, okay, process of Q of 0, the sensitive input here is Q of 0. Begin, process begin. Then as usual, the way how the clock signal, whether the falling edge instant is or not, is there or not, that we checked in previous one. Thus in the same way here also you have to check whether the Q of 0 is at the falling edge or not. Okay, so if falling edge of Q of 0, then same. Again it had to check the x value. If x value is 1, then its Q of 1 now becomes not of Q of 1, otherwise no. And if this end if is for this one, and end process like that, and finally the end of the architecture name. Okay, so like that we can write the digital representation for the asynchronous 2-bit counter. Okay, so if you observe here we have two process statements, one process statement for the first D flip-flop and another process statement is for the second D flip-flop. So it is not the case in case of the synchronous model. So in synchronous model, the same clock signal is used simultaneously by all the elements of the counter. Whatever the number of flip-flops presented in the counter, all the flip-flops use the same clock signal. Okay, but here, so the first D flip-flop uses the system clocks or system generator clock signal, whereas second D flip-flop uses the output of the first flip-flop as a clock signal. Okay, that is the difference you need to identify in the synchronous and asynchronous case. Okay, thank you.